But this week, we'll talk about the most important case, the normal distribution. All this week, we'll talk about the normal distribution. So for the last of the 7 distributions we look at, so to start with, let me look at the following function and its properties. The standard normal density function. Well, that's just its name. I mean, any properties we're going to have to derive. Phi of x, lowercase Greek letter phi. There's also going to be an uppercase phi. 1 over the square root of 2 pi e to the minus x squared over 2. Well, why? Why that square root of 2 pi? Well, let me talk some about this function. Here are 5 properties. It's always, well, first of all, it's an even function. Because that means that phi of minus x and phi of x are always the same. Because x occurs only as x squared here. So that tells us right off something about its graph, namely its graph is symmetric about the y-axis. Well, so let's figure out what the graph looks like using the usual Math 3A methods for graphing a function. We want to see what the graph of this looks like. Well, phi of x is always positive, strictly positive. It's never 0, because the exponential function is always strictly positive. And at plus or minus infinity, well, this exponent is going to minus infinity. So phi of x goes to 0, both at plus infinity and minus infinity. Well, so that tells us what the graph is going to look like at the far left and the far right. We'll also want to know where it's increasing and decreasing, concave, up, down, the usual things to draw the graph from Math 3A. So let's look at the derivative, phi prime. Okay, so the exponential function is its own derivative. And then the chain rule, we take the derivative of the exponent there, minus 2x over 2. Well, simplifies just to minus x. Well, so this is minus x times phi. So phi is always positive, and so the derivative is either positive or negative depending on what x is. if x is negative. Okay, so for the left half of the picture, if x is negative. Okay, so minus x is positive. Phi prime is positive. That tells us that the function is increasing. And for the right half of the picture, 0 to plus infinity. Okay, so now x is positive, minus x is negative. Phi prime's negative. We know the function is decreasing. Well, so it's got a maximum at 0. Because to the left of that it's increasing, and then it starts to decrease. Let's look at the second derivative to see where it's concave up and concave down. Well, so the first derivative is minus x times phi. So let's differentiate that again using the product rule. Minus 1 times phi of x minus x times, and then we'll differentiate the other factor. And since we know that phi prime is minus x times phi, let's plug in what we know. Phi prime is minus x times phi. And simplify this. We get the second derivative looks like this. Well, we know where that's positive and negative. In particular, it's going to be 0 when x squared minus 1 is 0. It changes sign, both at plus 1 and minus 1. So the graph has these inflection points. At minus 1 and at 1. Phi is always positive, but x squared minus 1 is changing sign at those two places. And it's going to be concave down between these two inflection points and concave up elsewhere. Well, that's enough information to get a pretty good idea of what the graph looks like. Symmetric about the y-axis. It's going off to 0 at the tails. It's increasing when x is negative. And for a while it's concave up, and then the second derivative changes sign. Got that inflection point here. Well, it's the famous bell curve. It's not a, okay, draw it more accurately. So it's got that maximum at x equals 0. Yeah, okay, the picture isn't perfect, but it's the standard bell curve. But I said 5 properties, and we're only up to 4. Well, property 5, which we're not going to derive, that the total area under the bell curve, the integral from minus infinity to plus infinity of the standard normal density function, is 1. Well, to derive this, we don't integrate over the line. We have to integrate over the plane, and we have to use polar coordinates that did not come up in Math 3AB. So we're just going to believe this, that it integrates to 1. So it can be a density function. It's a non-negative function that integrates to 1. It's a possible density function. And if a random variable that has this density function is said to have the standard normal distribution. A random variable z, okay, that's a capital Z, if it has density function phi, said to have the standard normal distribution. Later we'll look at cases where it's normal but not standard. Okay, so well, we'll also want the cumulative distribution function for z. So call that capital phi. That is, we want the function called capital phi, the function whose value at some number little z, okay, that's not a 3, that's a lowercase c. It's the probability that the random variable is less than or equal to z. Well, so that we get that by integrating the density function. So it's 1 over the square root of 2 pi minus infinity to z e to the minus so capital phi is this function, and well, that gives us an equation for it, and the picture well, lowercase phi gives us the bell curve, and capital phi for some number z is the area under this curve from minus infinity up to z. So it's that area, the shaded area in the picture. And to evaluate this numerically, what if we want to know what phi of 1 is? This is not a function whose antiderivative we can write down easily in terms of any functions we know. Luckily, there's a table in the book. Page 919, that gives gives us numerical values, tells us what phi of z is, at least for some numbers. Namely numbers between 0 and 3. Well, that will be enough, actually. We'll talk about what to do for numbers that are not in the interval 0 to 3. But yeah, e to the minus x squared over 2 is not something that has a simple antiderivative. The 1 over the square root of pi has to be there for property 5 to hold. I mean, it's a factor that's to bring the area down to 1. So instead of the square root of 2 pi. Well, suppose we have a random variable z like this, whose density function is phi. We can ask all our usual questions. Mean, standard deviation, probability of being within one standard deviation of the mean, the usuals. So suppose we have random variable z with a standard normal distribution. In fact, we're pretty much going to reserve the letter z just for this purpose and not use it for anything else. Its mean. Call it mu, or the expected value of z. Well, just from the picture, we figure the mean's got to be 0 by the symmetry. It's just as likely to be positive as it is to be negative. Yeah, by property 1 there, the density function is symmetric about the y-axis. Nonetheless, let's do the calculation and work it out. We know how to calculate the mean of a continuous random variable. We integrate x times the density function. Suppose we do that. We integrate x times the density function. Okay, so plug in the density function. Let's put the square root of 2 pi out in front. And this is not so hard to integrate. I mean, I was just saying that it's hard to write down an antiderivative for e to the minus x squared over 2. But this is an entirely different situation because we've got that x there and there's a substitution staring us in the face. So we do that. Now, first I'm going to break it in half. Instead of doing the whole thing, minus infinity to plus infinity, I want to put it in 2 steps. To make sure that everything's going to be okay. And now we're going to do this. We look at this, we have some function of x squared over 2 times the derivative of x squared over 2 cries out for the substitution u is x squared over 2. So du is 2x over 2. In other words, x dx. Okay, so we've got du sitting there. We're left with e to the minus u du. Now, when x is 0, u is also 0. And put that in the wrong place. Okay, when x is 0, u is also 0. And when x is going off to minus infinity, u is going off to plus infinity. So this first integral is going backwards from plus infinity down to 0. This one's going frontwards. Okay, and e to the minus u, we know how to integrate. So we do that. Minus e to the minus u would be an antiderivative for e to the minus u. And we plug in the upper and lower bounds integration. Well, so this first one, yeah, if we plug in u equals 0, we get minus 1 for the part in brackets there. Minus e to the 0, minus 1. Oh, and then we plug in u equals infinity, and we get 0. So I didn't even write that down. Well, we don't really plug in u equals infinity. We take the limit as u goes off to infinity, but that's 0. What about the other half? Well, we plug in u equals infinity, and we get 0 minus, and then we plug in u equals 0, and we get minus 1. So we have minus 1. Minus 1 plus 1. Well, we knew the mean was going to be 0. And we can do the calculation by working out the integral using substitution. What about standard deviation? Well, so the variance is the expected value of z squared minus mu squared, but mu squared is 0. The variance of z. Well, okay, the mean was obvious from the picture. The variance is not obvious from the picture. And so the expected value of z squared, we're going to integrate x squared times the density function. Let's put the constant out in front. X squared e to the minus x squared. Well, for the mean, it was a substitution, but now we look at this and decide what to do. And here's the plan. We'll do integration by parts. That x squared, x times x. So I'm going to write it like that. Well, that second factor, we know how to integrate. Because we just did it. We can integrate that second factor using this substitution. We get minus e to the u, minus e to the minus u. That is, here's an antiderivative for this second factor. That we worked it out over there, but we can check quickly by differentiating that the derivative of this, we get minus e to this exponent, and then we apply the chain rule. We get that minus x. So we can integrate that second half, and then integration by parts lets us differentiate away the first factor. Okay, so now we do it. We're just doing planning here. We apply integration by parts. So we have x times minus e to the minus x squared over 2. And we're going minus infinity to plus infinity. It would be perhaps wiser to break it down minus infinity to 0 and then 0 to plus infinity. But we're going to get 0 at all three places. Minus. Okay, now we get to differentiate away that x. So we just have 1, and then we have this minus. Okay, so this actually becomes a plus. E to the minus x squared. This first thing is 0. If you plug in infinity, so to speak, we get infinity times 0. Well, that's an indeterminate form, but we know what to do. We apply L'Hopital's rule. Again, and we get 0. Well, so leaving out some fine print there, this much is going to give us 0. And this is nothing but the integral of phi that's 1 by property 5 of our list of 5 properties. So we know the answer. The variance is 1. The standard deviation is 1. Now, what if we want numbers besides 0 and 1? What if we want some probabilities? Well, I mean, it's a wonderful formula, but if we want numbers, we probably will have to resort to using either the table on page 919 or a calculator with a phi button on it. I mean, not all calculators have the normal distribution built in, but your calculator might well have it. So as I said, page 919 has a table. And maybe one of those entries in the table we wouldn't need. 50, capital 50. We wouldn't need a table for that. That's got to be a half. Because it's right in the middle. Well, picture, it's right in the middle. 50 is that area right there. The entire area under the bell curve we said was 1. We've got half of it. But suppose we want suppose we have some numbers. And where z has the standard normal distribution, what if we want the probability that z is in that interval, 0 to 1.17? Okay, well, as I say, your calculator may have that built in, but you still need to know how to do the tables. I mean, for one thing, for our tests, you won't have your calculator with the phi button on it, and you will have a copy of the table. Well, step 1, maybe step 0. I mean, before we do anything, we'll draw the picture. 1.17, that's a little to the right of the inflection point. So we're after that area. And just from the picture, we know it's somewhere between 0 and a half, so we'd better get an answer in that interval. So what we want, well, part of what we want is the cumulative distribution at 1.17. That would give us, that's more than what we want. That's the area from 1.17 all the way down to minus infinity. So we want to subtract off the left half of that, 50. Looking in the table for phi of 1.17, it's 0.8790 to 4 decimal places. Now, how to use that table? There's a column down the left that gives, for the input z to 1 decimal place, and then across the top you look for the 7 column. So the 1.1 row and the 7 column has that number in it. And phi of 0 is a half. conclusion, the probability we want is around 38%. And but that was too easy, because that's just using numbers between 0 and 3. It's covered by the table. What if we want numbers not between 0 and 3? Well, first, what about big numbers? This number, that was 1. Suppose we want phi of z for where z is 3 or more. Well, our table only goes up to 2.99. That's as close to 3 as it gets, but it says that phi of 2.99 is. And of course, phi of z, even for larger z, is less than or equal to 1, in fact, strictly less than 1. Because it's a probability. And it's not equal to 1 because there's some tail left out. Our table only goes up to 3. What if we have some big number? Well, if we can at least say it's between 0.9986 and 1. There's not a lot of room between those two numbers. 0.0014 is how much room there is between those two numbers. So phi of z, if we take phi of z simply to be 1, that's correct to 3 decimal places. Just round this off to 3 decimal places, you're at 1. And we've got this number between 1 and 1. Three decimal places is about all we can get out of this table anyway, because we can only put in 3 significant figures max. Now, there are ways to get more accurate results. Your calculator may give something more accurate. There are calculators on the normal distribution calculators on the web that will give more accurate results. But for 3 figures, we can just take phi of z to be 1 if z is more than 3. What if z is negative? I said our table only applies to inputs 0 to 3. What about minus 2.5? Well, we use the symmetry. Before doing anything, we'll draw the picture. What if we want phi of minus 2? So that area there, phi of minus 2. Well, look at its mirror image. By the symmetry, the left-hand tail has the same area as the right-hand tail. Phi of minus 2 is this area on the right-hand side. And that's the complement of the area up to there. That is, this area is 1 minus phi of 2. Let's add another color to the picture. Phi of 2 is the red area here, all the way down to minus infinity. So what we want is what's not phi of 2, the right-hand tail. Well, that's looking at the complement of the event. The total area under the bell curve is 1, so we're taking 1 minus phi of 2. Well, there's nothing special about the number 2. Phi of minus a is 1 minus phi of a. And that lets us take care of negative numbers. And if we want the probability that the random variable is, say, more than 1.17, and a minute ago we were looking at the probability of its being less than 1.17. It's the number 4. The probability that z is more than 2, where z has the standard normal distribution. Well, that's the area we were just looking at. Z greater than or equal to 2 is the complement of z being less than 2. And because it's a continuous random variable, so it doesn't matter whether we have less than or equal to, because it's a continuous random variable. The probability of being exactly any one number is vanishingly small. And written this way, of course, it's 1 minus phi of 2. So we look in our table for phi of 2. Let's see, phi of 2 is 9772. It's already getting pretty big. So this would be 1 minus that. 0.228. On 2.25%. And same for other numbers. So suppose we want say we want to find the probability that z is in the following interval, where z has the standard normal distribution. And so here are some numbers. Minus 1.25 up to 0.33. Well, before we do anything, we'll draw the picture. Minus 1.25, that's a little to the left of the inflection point. 0.33, that's right up there. we're after this area. Well, of course, so that's phi of 0.33. That would give us way too much. Gives us everything from 0.33 down to minus infinity. So we'll subtract off phi of minus 1.25. Well, that's a negative number, so we'll have to think of it as 1 minus phi of 1.25. And then now we just have numbers between 0 and 3, so our table will handle those. Phi of 0.33, we look in our table, it's 0.6293. Phi of 1.25, well, that's going to be more, 0.8944. And then we do the arithmetic, right? Addition, subtraction. We get a little bit more than a half. Yeah, so our table lets us do problems we want with the cumulative distribution. We have not yet done the usual problem. What's the probability where z has standard normal distribution? The probability of being within one standard deviation of its mean. Well, for the standard normal distribution, the mean is 0, and the standard deviation is 1. So we're asking for the probability that z in absolute value is less than or equal to 1. Before doing anything, we draw the picture. We want the area under the bell curve between the two inflection points. So we're after that area. So that's phi of 1 minus phi of minus 1. Well, phi of 1 we can look up. Phi of minus 1, we have to think complement, 1 minus phi of 1. So we have 2 times phi of 1 minus 1. And then we look up to see what phi of 1 is. 0.8413. We double that and subtract 1, we get about 68%. 683. 68% chance of being one standard deviation of the mean. Well, we've done, it's a little different from what we got for the exponential distribution and some of the others. We'll do some more of this next time. Got to stop.